Greetings, this is Dr. McCrenner, and this lesson is part of EVE385, Engineering Hydrology, also known as the Stormwater course. And what I'm going to be covering in today's lesson is the hydrologic cycle and hydrologic balances. So hopefully, prior to watching this video, you covered some material from the Blackboard lesson. You would have looked a little bit at the water cycle from a couple of resources. You have read an article about climate change and the hydrologic cycle and how that is being impacted. And then you would have reviewed some parts of the text. Okay? Chapter 1 gives you an overview of hydrology as an area of study, and section 7.1 gets into hydrologic balances. So what you should be able to do at the end of this lesson is, first of all, to identify and define the components of the hydrologic cycle. Hopefully you'd be able to do that pretty successfully at this point from the preparatory material. Second thing you need to be able to do is write hydrologic mass balances. Okay? And you may have some success with that. I know in some areas of those preparatory materials you'll have seen that. And then third, you need to be able to solve hydrologic mass balance problems. And I don't think you saw much of that in the preparatory material at all. An important note here is that for hydrology, stormwater, water density can be assumed to be constant, so a volume balance, which is what we're going to be working at, is the same as a mass balance. And that's because mass is density times volume. Oh, and you will be getting a complete collection of these slides that I'm working on along with this lesson. So you're going to get a blank set. You can note it as you want, and then also be saving this with my annotations so that you have a copy of that. So if you can't read something quite perfectly or you're pausing and restarting a lot, know that you will get this with all of my hand notes on it. So the hydrologic mass balance from May's text is hopefully something you would have seen. And this is a macro scale, kind of large area and also large time, and I'll mention a little bit later what we're referring to there, balance for hydrology. An important thing is that they've normalized all the numbers relative to 100 for the rate of precipitation. So while we don't, and that's precipitation on the land, okay? So we don't have exact units here, but they've been normalized to 100 based on precipitation on land, so you can kind of put any set of units on those at a level that you really want to. And then you'll notice that he's got evaporation coming off of the land, evaporation and evapotranspiration. Transpiration is the release of water from plants. Then we have moisture that moves over the land. We have from the ocean, so we've got evaporation from the ocean coming up. Some of it will move over the land to become precipitation. Some of it is just going to precipitate back over the ocean. And then he has an important one here for us. This will be one of the big things we're going to look at is this surface outflow. Okay, that's our runoff. He's got groundwater outflow. Sometimes this is called base flow. Okay, we're not going to do much with that in this course. We'll probably mention it from time to time. And then he has a variety of other processes listed in here. Okay. And actually that one should not be a process. Okay, he's just locating actually where the water table is, and you'll notice that water table level is the same as in his reservoir. And then I thought it'd be useful for you to see that these hydrologic balances are similar across other textbooks. So this is a text we've used in the environmental engineering program before from Huang and Houdelin on hydraulics and a little bit on hydrology. And you'll notice that again, we've got your precipitation, we've got the evaporation over the ocean, we've got the transpiration, evaporation on the land, evaporation off of rivers and lakes, so the difference coming off of the soil versus coming off of a free water body. One of the things that is added in here is snowpack. Being that we're in Georgia, we're not going to do a lot of the hydrology on snowpack, but if you're out west, it is a big deal. Then we have an aquifer down here, and you have flow associated with it. This would be your groundwater or base flow. Okay. And we again see infiltration, which is going to be another important term for us. Okay. Then this is out of Juanalista, Kirsten, and Eaglin, which is a nice text as well on hydrology. And I've chosen to use this because I've really set this up from sort of an engineering perspective with a set of boundaries. Okay? So if we look over here at the left, we have a boundary, and so anything coming in by nature, we've got a downsloping land, so water will be moving in across that boundary. And on the right side here, we have an outflow boundary, because of the nature of how this is set up. We would have flow across that, flow out that way, since it's downsloping. And one of the things you would have base flows down here, which in some cases you would need to consider. Okay. That subsurface type movement, we're not going to be focusing on that in this class really at all. We're going to mention it so we're aware of it, and you're not surprised when you hear that term if you graduate. Okay. When we look at this, one of the things we want to be able to do is write what I'm going to refer to as a macro timescale hydrologic balance. Sorry, having a little tech difficulty here. There we go. Slide all that down. Good. So when we talk about macro timescale hydrologic balances, this is times that are greater than at least a week in general. We'll probably do some things where we may do this on a daily basis, but really the time when you're going to do the macro scale, it's at least a week, and you're probably looking more at like, monthly or yearly type time periods. Okay? And generally, these are for water planning. Trying to figure out what your overall budget is and what's going on with that. So when we want to write a mass balance for this, we need to incorporate pretty much all of our different terms. Okay? So in this case, we would have our boundary input, okay, is coming into there, and also, and what we're going to say, surface here, okay, plus the boundary input that is subsurface, plus our precipitation. Okay, so those are all things that are coming into the system. Now, when we look at this, that is all going to be equal to, okay, rainfall excess and that's also called our runoff, plus storage, okay, plus infiltration, plus evaporation, plus evapotranspiration. Plus our boundary out surface and our boundary out subsurface. And I do not think I have missed anything there. Nope. Okay, so that is kind of a mass balance on a large system, large time step where you'd be doing hydrologic planning. And our first set of problems are going to be kind of focused on this type of setup in general. Okay. We also need to be able to do micro timescale hydrologic balances. And these are short time step, or short time, which is approximately a day or a storm event or a linked series of storm events. Okay. So those three things. So we have a day, a storm event, or a linked series of storm events. And I use that term linked because basically it means there's not much time in between them. You wouldn't use this if you had a storm event on Monday and another one on Friday. Those aren't linked. But if you had a big storm event Monday, a couple hours later, Tuesday, you have another storm event, those would basically be linked, and you could use this type of hydrologic balance on them. So for this case, I'm going to eliminate base flow. Okay, so we're going to disregard base flow. And so our boundary input up here is runoff inflow. Okay. And our boundary output here, we're going to call runoff outflow. And the area in between these two vertical lines is our development, our area of interest, our property we need to evaluate for this event. So our inputs to the system are going to be the runoff inflow plus the precipitation. So that's what we're putting in to the system. Then our removals from the system, because it's short term, okay, is going to be infiltration, that part of the rainfall and inflow that infiltrate, move into the subsurface, plus storage, plus depression storage, and we'll mention a little bit more about that in a moment. Okay, infiltration storage and depression storage, plus the runoff outflow. Okay, so in short time periods, evaporation and evapotranspiration and transpiration do not have a large impact. So those are the primary things we're leaving out. Now on this depression storage, it is called initial abstraction, is the fancy word for it. And it's basically storage in puddles. And so it will not run off. Okay. But it can infiltrate or evaporate. Okay. So it can be removed later on. You know, puddles go away after the storm, but that's what we're talking about with initial abstractions. Okay? And then commonly, we will rearrange this because what we really need to know is our runoff outflow, and that's going to be our inputs, which would be runoff inflow in this case, plus precipitation, and then we remove from that storage, depression storage, and infiltration. So you want to note that that negative is going to distribute across all of that. Okay. So across all of these terms. So you would add the runoff inflow and precipitation, subtract storage, subtract your depression storage, and subtract your infiltration, and that will give you an estimate of what your runoff outflow will be. And so from here, we're going to work a couple example problems. So first example problems, and these are again included in the handout you receive, or that you can choose to print out, is we have a lake, okay? It has evaporation off of it of 3 meters, and its area is 1,600 hectares. Okay? So you're going to get to use a lot of units that you haven't used in the past, and unit conversions are going to be critical in this case, in this class. So you'll have to follow those through. And then, so we want to find the total value of evaporation, and we want to find it in cubic meters, average daily evaporation rate, millimeters per day, hectare centimeters per day, and cubic meters per day. Okay, so when we take a look at this, the surface area for evaporation is 1,600 hectares. Okay. Now, a hectare is a metric acre. And 100 hectares is 1 square kilometer. Okay. The total annual evaporation is going to be the 1,600 hectare surface area of the lake multiplied by the 3 meters that evaporate off of it, which gives us 4,800 hectare meters. Okay. And notice this is an area, the hectares, multiplied by a length. So that is a volume. Okay? And so we're going to have some units that are going to make you a little bit uncomfortable. In some cases, we're going to use length as a volume. Okay? And we're going to do that in a moment. There's some important, it's a very useful tool in hydrology. There are some caveats you're going to have to learn about it as to when you can and cannot add those, and when you should be using which type of unit. That's one of the things that comes out of this course. Now, you'll notice you were asked for this in cubic meters. We don't have that. So we're going to need to convert this. Okay? 4,800 hectare meters. And if you're not used to doing conversions like this, I encourage you to start getting used to it, because it will help you avoid a lot of simple, silly mistakes. Okay. And hopefully you have all seen this type of unit conversion before. One of the things I do miss when doing these video lessons is that I don't have you there to correct me when I make little errors like that. So I do try to pre-work all this stuff. And then this is squared. Okay. So before we do any calculations, we're going to want to check that we get left with meters. So we have a hectare here we can cancel out, and then we have a kilometer, and it's going to be squared, and a kilometer squared to match off up there, because we'll end up with meters squared, so we end up with cubic meters. And so we would have 4.8 times 10 to the 7 cubic meters of evaporation off of that lake in a year. Okay. So now we want to find the daily evaporation. Okay. So in the daily evaporation, we have 3 meters per year of evaporation off of that lake. Then a single year has 365 days in it. You know, it can be argued that there should be a decimal there since we have leap years, but we're going to ignore leap years, consider them negligible. And then there are 1,000 millimeters in every meter, okay, which gives us a daily evaporation average of 8.22 millimeters per day. And we wanted that in millimeters per day, hectare centimeters per day, and cubic meters per day. Okay. Well, if we want to do cubic meters per day, actually I don't think I calculated that one, so we'll have to do that. We know that we have 4.8 times 10 to the 7 cubic meters every year. And then we would have that same set of multiplications, and it will equal something over here. So I can leave that for you to calculate out. The last one, we have 4,800 hectare meters of evaporation every year. We again have the 365 days in a year. And there are 100 centimeters in every meter. So we have 1,315 hectare centimeters per day of evaporation off of that lake. So the second one we have is a runoff situation where we have runoff from a 6.7 acre parking lot. It's in Chicago, Illinois. That's not critical to us, but we know that the average runoff is 20 CFS for a 2-hour period. So what we'll find out later when we start working these types of problems is runoff from an area will vary over time, okay? But there will be an average runoff rate and a time period for the runoff. So the average runoff rate from this parking lot was 20 cubic feet per second for a 2-hour period of time. There are 0.08 inches of depression storage on the parking lot. Okay? What we want to try and figure out is the volume of rainfall. Okay? And then we want our answers in inches, acre feet, and cubic feet. Okay? So the first thing we need to do is write a mass balance. And the mass balance for this, since a parking lot is basically impervious, which means no infiltration, precipitation is equal to the runoff plus the initial abstraction, which is our depression storage. Okay? The area is the 6.7 acres, and there are 43,560 square feet in every single acre, and 640 acres is a mile squared. The runoff is 20 CFS for 2 hours. The initial abstraction is 0.08 inches over 6.7 acres. So the precipitation is going to be 20 cubic feet per second times 2 hours times 3,600 seconds every hour. So that'll leave us with units of cubic feet. Then we have 0.08 inches of depression storage times 6.7 acres times 43,560 square feet in every acre. And there's a foot in every 12 inches. So we know that is there. If we glance over here, we notice the hours are going to cancel, seconds will cancel, and there. Inches cancel, acres cancel. So we have cubic feet on both sides of that. We end up with our precipitation is 144,000 cubic feet of runoff plus 1,900 basically cubic feet of depression storage. Okay, so that depression storage is a real number. Is it significant compared to the runoff? No, but it ends up being a real number for us. So we have 145,946 cubic feet of runoff. And so that answers part of our question, cubic feet. We now want to express that in inches and acre feet. So to get this into acre feet, we would have 145,946 times, that's cubic feet, times 1 acre in every 43560 square feet, and that will yield for us 3.35 acre feet. If we divide that 3.35 acre feet by the 6.7 acres of surface area we're dealing with, and then we multiply by the 12 inches in every foot, that's going to give us 6 inches. So we had a storm event of 6 inches on that 6.7 acres of parking lot. Now, switching the problem up a little bit, this time we have the rainfall on a 20-acre watershed. We want to figure out the rainfall excess if 30% of the watershed area is a lake and the infiltration on the soil is estimated to be 1 inch. Now, this is a neat problem in that the condition of the lake ends up being very important to us, okay? Because the lake condition is how much rain on the lake will be stored. Okay? So the condition of that lake is important to us. Okay? I'm going to make our notes here with our data. Okay? So the watershed area is 20 acres. The lake is 30% of the watershed. Which is to say that there are 6 acres of lake and 14 acres of land. The precipitation is 3 inches. Infiltration, you're gonna love this, it's commonly defined with a capital F when we're talking about a volume, is 1 inch. Okay? And we're gonna assume that runoff is not routed into the lake. So, the first case we're going to look at is the lake condition that there are greater than or equal to 3 inches of storage available. Okay. So that means rain on lake is stored. So the rain runoff is going to be precipitation minus infiltration minus the lake's effect. I'm pretty sure that is effect with an E since it's a noun. Or should it be lake effect? Because it's a verb. Could say the effect of the lake. Not sure. It's an A or an E. It's one of those things I always struggle with. Have to look up commonly. So, when we look at this, we have 3 inches of rainfall, okay, on the 20 acres minus 1 inch, there's a decimal place there, 1 inch of infiltration on 14 acres, okay, minus 3 inches on the 6 acres of lake. And you'll notice this can actually be reduced down to being the same thing as 3 inches on 14 acres minus 1 inch on the 14 acres. And then we can reduce that further to 2 inches on the 14 acres. Okay. So we end up with, then we'd have to multiply that by 12 inches for every foot, and that will yield for us 2.33 acre feet And, oh, good, 2.33 acre feet. And that is equal to 101,640 cubic feet. Okay. But we also wanted to calculate the runoff in inches from that 20-acre watershed. Okay, and this is where the use of inches can become difficult for you. If we have 101,640 cubic feet, and we have a 20-acre watershed, and there's an acre in every 43,560 square feet, and 12 inches in every foot. My calculation here is 1.4 inches. Okay. So it's important to notice that these numbers can be a little deceiving. Okay? But when we're talking about that 20-acre watershed, we would have 1.4 inches of runoff from it. Second lake condition. It's full. No storage available. That means all precipitation on lake is runoff. There's a little something there from when I created these. It shouldn't have shown up. Okay? So when we take a look at this particular case, our runoff is our precipitation minus infiltration minus the lake effect. And in this case, it's actually going to be a plus the lake effect. Oh, I'm sorry. It should not be a plus the lake effect. It is a minus the lake effect. Okay. So the runoff is our 3 inches on the 20 acres, okay, minus the 1 inch of infiltration on the 14 acres. And then we have no reduction in runoff associated with the 6 acres of our lake. So we end up with 3.83 acre feet. I left out the unit conversion there. And that is 166,980 cubic feet. So our runoff in inches is going to be 166,980 cubic feet divided by the 20 acres, multiply by the 43,560, put that in the wrong spot, the acre for every 43,560 square feet, and 12 inches in every single foot, which gives us 2.3 inches of runoff. And the final lake condition there is some storage available. And we will call that X inches storage on the lake. That means our runoff is going to be, again, the precipitation minus infiltration minus the lake effect So it would be the 3 inches on the 20 acres minus 1 inch on the 14 acres minus X inches on the 6 acres. So our runoff will be 46 acre inches minus 6 acres times X inches. And then we could do unit conversions out from there. I can give you an example calculation for X equals 2 inches. R is 2.83 acre feet, 123,420 cubic feet, or 1.7 inches. Okay. I think we have 2 more of these, so if you want to take a break, you can always hit pause, walk away, come on back. Okay. Unfortunately, I've got to keep plugging away at them, but we're almost there. So this is a reservoir type problem where we need to evaluate a reservoir. So water is going to be supplied from a reservoir that is fed by a stream. So we have a reservoir fed by a stream with a discharge of 2 cubic meters per second. And we want to meet the demand of a community with a population of 150,000. They consume 300 liters per person. Lowest discharge of the stream is 0.25 cubic meters per second for a period of 15 days. Okay? So basically we want to make sure that for that time period where we have a low inflow, okay, we have enough storage to meet the supply of the community. Okay. So reservoir should have enough capacity to supply demand during low flow periods. Okay. Now the community demand is going to be 150,000 people consuming 300 rather liters per person day. And there are 1,000 liters in every cubic meter. which gives us a demand of 45,000 cubic meters every day. Okay. And then the lowest inflow rate is 0.25 cubic meters every second. Okay. And we have 3,600 seconds in all of our hours and 24 hours in all of our days, which yields 21,600 cubic meters of inflow every day. So our deficit, our flow deficit, the flow deficit is 21,600 cubic meters of inflow minus the 45,000 cubic meters of consumption, which gives us a negative 23,400 cubic meters per day. Okay. And we'll notice because of how we phrase that, I mean, it could be argued that that should be a positive number because a negative deficit is a surplus, but we know that as engineers we can think about numbers, understand what they mean. Basically, our community needs to come up with 23,400 cubic meters every day of water, okay, that we are short because our stream's inflow is small. So the deficit flow period, the deficit period, is 15 days. So the deficit volume is going to be the 23,400 cubic meters per day for that 15-day period, which means we need to come up with 351,000 cubic meters of surplus from our reservoir. Okay. So the reservoir storage volume is 351,000 cubic meters. Okay. I think that gets our first question. Check, reservoir size. Okay. And then we need the normal area in kilometers squared of the reservoir if its depth is 10 meters. Okay. Now I use that term normal area because our pond or our reservoir is not going to be a perfect cylinder or a perfect cube, that kind of shape. Okay, we're not going to have a situation where the base area and the top area are the same. We're going to have a situation where we have a surface area, a bottom area, and somewhere in between those two, there's our normal kind of average area of the pond perpendicular to the depth. Okay. So this is what we're looking for right there. Okay. So basically the average cross-sectional area of the pond. So if we have 351,000 cubic meters times this area normal multiplied by the 10-meter depth. That means our area normal is going to be, oh, I think it asks for it in a different set of units. Yep, you want to find that in kilometers squared. So our area normal is going to be 351,000 cubic meters divided by 10 meters. Okay. And then there are 1,000 meters in every kilometer, and we'll square that to make our units work out, which means we have 35 thousandths of a kilometer in average area. Our next question is the surface area of the reservoir, assuming the pond's bottom area is half of the surface area. Okay. So the surface area, change the colors here again, find surface area if area of the bottom is equal to area of the top, which is the surface, over 2. Well, the area normal is the area of the top plus the area of the bottom all over 2. Okay. Which means in the numerator here, we would have top, area bottom, boom. We would have 1.5, the area of the top, over 2, which is 0.75 area of the top. And so that's going to give us the area of the top is 0.047 square kilometers. Okay, so, and as we should expect, it's larger than the normal area. If we were to calculate the area of the bottom, it would be smaller than the normal area. And the last question we have, so we've got, pardon me just a second. The last question we have is the rate of outflow when the reservoir is full. Outflow rate from reservoir when full and not in deficit. Okay. Well, the normal inflow is 2 cubic meters every second. And again, our conversions that we'll have here. So we have 172,800 cubic meters of inflow every day. Q out is going to be that inflow minus the community demand and that will be with some conversions. So let me put this here, and then we'll have conversions. And that will yield 1.48 cubic meters per second of outflow. All right, almost there. One more, I think just one more example. Is it two? It is two. I got very ambitious in preparing this lecture. One of them's short, one of them's just a little bit longer. So there's a reservoir with a surface area of 20,000 hectares. The reservoir is initially dry. It's got an average annual water depth of 5 meters. We've got a drainage basin that supplies water to the reservoir. And we have some losses from the annual precipitation. And so we want to find our average annual precipitation in meters. So the reservoir surface area is 20,000 hectares. Again, those metric acres. We're calling that 100 hectares is a single kilometer squared. And that means that this then is 200 square kilometers. Okay. The reservoir storage is 5 meters. Okay. This is also 5 meters times our 200 kilometers squared. So this time we're assuming that there is no slope to our reservoir. And the area of the top and the area of the bottom are the same. There's 1,000 meters in every kilometer. We'll have to square that. So our available storage is 1 times 10 to the 9 cubic meters. Okay. The drainage basin area is 100,000 hectares, which is 1,000 square kilometers, which is 1 times 10 to the 9 square meters. Now the reservoir storage is equal to the watershed runoff. So we have 1 times 10 to the 9 cubic meters of potential storage, and we have 1 times 10 to the 9 meters squared of watershed area multiplied by the runoff from that. So the runoff is a single meter from that watershed. Now from the ratios we were given, we know that 20% of the annual precipitation is lost to, what do we have there? Evaporation. So we've got E, evaporation, T, transpiration, F, infiltration, and S. There are no storage losses. And storage. Okay? So all those are losses, which means 80% of P is runoff. Okay? So R is equal to 1 minus 0.2 times P, which means that precipitation in that area is 1.25 meters every year. Now, a note here for this particular problem is it could be reworked assuming P on the reservoir also supplies the reservoir. But I think you can kind of look at this and see that the way this particular example was set up, if it had been worked that way, our numbers would have been a little bit odd, okay? Because we already have, I mean, little over 3 feet of precipitation, which is a fairly small amount. And our final problem here, the Little Joe Creek problem, okay? So we've got a lot of data in here, lots of unit conversions, okay? So we've got Little Joe Creek. Why don't you hit pause and read this, and I'm just going to get right into working the problem. So the worst data on record for a given 12-month period precipitation is 20 inches. Lake evaporation is 58 inches. The required outflow is 5 CFS. The reservoir surface area is 640 acres. The watershed which is to say the supply area is 3,840 acres. The runoff rate is 0.5 cubic feet per second per mile squared of area. And we should note here there are 640 acres in a single mile squared. The irrigation demand I should say brackets there, it's demand. We have 700 acres at 3.5 feet of irrigation per year. Okay. When we sort out our units there, we will end up with 1.07 times 10 to the 8 cubic feet every year. Okay. The wetlands are also a demand. And they have 100 acres of wetlands, and they need 9.6 feet of supply on their area every year, and so that is 4.18 cubic feet every year. There's conversions in here I'm again leaving out. Our reservoir calculations precipitation which is an inflow or supply, is 20 inches per year times, we've got a foot in every 12 inches. We have 640 acres, and we have 43,560 square feet in an acre, which yields 4.65 times 10 to the 7 cubic feet every year. And then we have our evaporation, which is an outflow. Outflow probably isn't the best way to phrase that. We should just look at that as a loss. Okay. Evaporation, which is a loss, and that rate is 58 inches in a year. We have all those same unit conversions, which yield for us 1.35 times 10 to the 8 feet cubed per year. And then we have water rights. That's an important issue in reservoirs anymore, because you put a reservoir in and you can certainly take the water from the people downstream. In the Old West, people got killed over that, damming up a river so that the people downstream didn't get water. Okay? And that is 5 cubic feet every second. We have our seconds per hour, our hours per day, and our days per year, and that will yield for us 1.58 times 10 to the 8 cubic feet per year. Then we have watershed runoff, which is an inflow or supply, and that is 3,840 acres at 0.5 CFS for every square mile. And so we're going to have some conversions in here. And that will yield for us 9.46 times 10 to the 7 cubic feet per year. So then our ungauged flows must be equal to our outputs minus our inputs. Okay. So the outputs, you can backtrack through all this. We have 1.58 times 10 to the 8 plus 1.35 times 10 to the 8 plus 4.18 times 10 to the 7 plus 1.07 times 10 to the 8. Those are all the things that we would consider our outputs. Our inputs are going to be 9.46 times 10 to the 7 and 4.65 times 10 to the 7. These are all in cubic feet per year. Cubic feet per year, which means our ungauged flows are 3.01 times 10 to the 8 cubic feet per year, and that is 9.54 CFS. So a lot about that watershed we don't know about. And let me switch over to this. So this is Dr. McCrenner. I'll try to be a little less enthusiastic maybe in the future with some of my example problems. And before we go, I just want to remind you to keep your head above water.